Welcome back. We started off this semester by looking at the principles of translational motion. We just finished learning about rotational motion in the last couple of chapters as well. We're now ready to tie the two types of motion into one physics problem. We're going to do this by exploring static equilibrium problems. In Chapter 9, we will learn about static equilibrium, which happens when translational and rotational motion balance to zero. And we'll also discuss the stresses and fractures in objects when they are not in equilibrium. In the first video here, we're going to look only at static equilibrium. We'll begin by looking at what conditions are needed for an object to be in equilibrium. We'll then learn how to solve these equilibrium problems and then finish by making an application to muscles, joints, and balance. Back in Chapter 4, we learned about Newton's second law. The total force is equal to the mass of an object times its acceleration. This figure shows a book on a table. It is not moving, so the acceleration is equal to zero, meaning that the total force has to be equal to zero. This is what we mean by equilibrium. All forces add up to zero. Equilibrium is a Latin term meaning equal forces or balance. We can look at this in two dimensions as well. Recall from our free body diagram problems in Chapter 4 that when we solve a two-dimensional force problem, we apply Newton's second law not just once, but twice, once for each component. We do the same here, but the acceleration in both directions is equal to zero. In other words, the object is not moving in either the x or y directions. Mathematically, that means that the sum of forces is equal to zero in both the x and the y directions. If we were dealing with a three-dimensional problem, then the sum of forces is equal to zero in x, y, and z directions. In addition to translational motion, we also have to worry now about rotational motion. An object could have no translational motion, but still have translational motion. In this figure, the total force on the ruler is zero, since the forces are equal and opposite each other. But because of how the forces are placed, they cause this ruler to rotate. So to truly be motionless, we need translational and angular accelerations to be zero. In other words, we need the sum of forces and the sum of torques to equal zero. These are the two conditions for static equilibrium. Our choice of the rotational axis is arbitrary. We can set our axis of rotation wherever we want on this ruler. If the torques around that point balance to zero, regardless of the center of rotation, then the ruler will remain truly motionless. To solve a static equilibrium problem, begin by choosing an appropriate coordinate system to solve your problem. Set the origin at your chosen axis of rotation. Remember that the choice of rotation is arbitrary. So if we choose the axis cleverly, then it can simplify the problem. I'll show an example of this in the next slide. After you have chosen your axis of rotation, you'll want to draw a free body diagram showing all the forces in the pictures. If you include where the force is being applied, drawing your force vector at the appropriate distance r from the origin, then you can also calculate the total torque. Once you know what forces are involved in our system, apply these forces to our equilibrium equations for forces and torque. Finally, plug in your numbers and solve for the missing variables. These are great steps, but these steps may not fully solve all problems. In real problems, the setup may be more complicated, but these steps will be good to at least start the problem, and then you can use your knowledge of static equilibrium to complete the problem. For example, imagine this problem where a copy machine is sitting on a desk as shown. Right away, we know there are four forces on the table: the weight of the table itself, the weight of the copy machine on the table, and the forces the legs apply on the table, FA and FB in this picture. The first step to solve this problem is to choose a coordinate system. We could just choose the center, but if we are clever, we can simplify our problem. With this setup, we have a torque exerted by both FA and FB. But if we choose our axis of rotation around the left leg, then the torque due to force A is equal to 0. This will greatly simplify our sum of the torques equation and thus simplify the whole problem in general. So the free body diagram would look just as we showed here in the figure. Force A pointing up at the axis of rotation, the weight of the table, which we'll indicate with lowercase m times g, at the distance of 10 meters, the weight of the copy machine, which we'll indicate with the uppercase m times g, at a distance of 15 meters, and the force of the right leg upward at the other end of the table, 20 meters away. Knowing these forces, we can then apply them to our static equilibrium equations. There are no forces in the x direction, so we can skip that. The total force in the y direction would then be force A, which is upward, minus the two downward forces, little mg, which is the weight of the table, and big mg, which is the weight of the copy machine, plus the upward force B. The total would have to be 0. We can then use this to solve for the missing variables, but we can't solve for anything yet because we have two unknowns, FA and FB. This is often the case, so we need the sum of torques as well. In our torque equation, we account for a torque for each force in the picture. Force A, the weight of the table, weight of the copy machine, and force B. But remember that because we chose our coordinate system, so its origin is on force A, then the torque due to force A is equal to 0. There are only then 3 torques around the axis that we have to worry about. The weight of the table would cause the table to rotate clockwise around the axis, so it is negative. The same applies for the weight of the copy machine. The torque due to force B would cause it to rotate counterclockwise, so it is a positive torque. These torques added together must equal 0. When we substitute the torque for its definition of radius times force, then we get an equation where we know absolutely everything except for force B. Then using these two equations we just derived, we can solve for FB using the second equation and then we can calculate FA by using the first equation. When choosing the directions of each force, you may need to infer the direction of a force. In other words, you may need to guess what direction the force is. When this happens, don't be too worried about what direction you set force A and force B to be. In this figure, let's assume that we set force A and force B to be upward. When applying these to the torque equation, setting the axis on force A, then we get a situation that we would expect. The board pulls down and leg B pushes up, balancing each other and holding the board steady. And thus you attain static equilibrium. But this needs to be true for any coordinate system. Let's move our coordinate system so that it's on leg B. You'll find that this won't work anymore since force A and the weight of the board both apply a clockwise rotation, making it impossible to achieve static equilibrium. Math, however, comes to our rescue. Since we chose FA to be in the wrong direction, the math will come out so that the force will be negative. If you do your math and you find that the force is negative, that just indicates that that force is pointing in the opposite direction from what you defined. So solving this problem, I defined FA to be upward. If I solve it, I will find that FA is negative, which means really FA is a downward pointing force. Don't worry, it'll work out, I promise. So this really is a trivial fix. Don't get too hung up about it. It will work out. Let's look at a slightly more complicated problem. Here you have a cable holding up a sign. Since the cable is attached to the pole at an angle, the force of tension can only point in a direction along the cable. This means that now we have both x and y components to our force equations. So now our two static equilibrium conditions look like this. The first condition is that the sum of forces, two dimensions, is equal to 0. And the second condition is that the sum of torques is equal to 0. Since the sum of forces is in two dimensions, we break it into two one-dimensional problems. And now we have three equations that we can work with. Okay, that teaches us about the two main conditions for static equilibrium. Sum of forces is equal to 0 and sum of torques is equal to 0. We can actually use these principles to understand the forces within the body. Here's an example of an arm bent at a right angle. What you see is that the weight of the arm and the weight, any weight on the arm, in this case a ball in the hand, both of those pull down on the arm, causing a clockwise rotation, in other words, a negative torque. But you have a bicep, which is attached very close to the elbow. It exerts a force upwards, causing a counterclockwise rotation, or a positive torque. And so all of these have to balance. But what if I bend my angle at a different angle, such as this 45-degree angle on the right side of your screen? Well, then the force on the muscle still has to pull upward and still needs to balance the torque. This can be very useful when we talk about, say, physical therapy or weight training. We want to know the ideal place to put a weight that will maximize the force needed by the muscle, and thus exercising the muscles as best as you can. Also in physical therapy, you may want to consider not too much torque by the ball. So you may want to place the weight closer to the elbow, and thus you'll exercise the muscle without exerting too much force during therapy. Here's another good example for a chiropractor to be looking at. In the left, you see a man who is kind of hunched over, but that particular position where he is exerts some really nasty forces on the spine. Look in the middle figure. You have WT, which is pointing downward in the middle. That's the weight of the torso, or the trunk of the body. WA, which is the weight of the arms, pulling down slightly higher than that, plus the weight of the head. That's the WH in the picture. All of those are pulling down at the spine. And so in order to straighten up, the muscles in the back have to counter that torque. And you can see the interesting angle that that muscle has to pull at, only about 12 degrees off of the spine. And so that that force from the muscle has to be quite large in order to keep balance and to keep the body stable. So the applications of static equilibrium really do apply very closely to the body, to muscles and forces exerted by the muscles. Overexertion can definitely be a worry, and so it's definitely a concern that every physical therapist, chiropractor, every medical doctor really needs to be aware of. In the next couple of videos, we'll look at a few examples of solving static equilibrium problems.